saw blade on there. All right, we're going to finish 12.8 and talk 12.9. So before we move on from this start slide, the big thing that we're going to get to in 12.9, which is honestly easier than 12.8, like 12.8 was complex numbers, that's probably one of the hardest sections of this entire year. But when we look at different graph types, they really mainly fit into three different categories. We have linear, quadratic, and exponential. So linear you guys dealt with in 7th and 8th grade math. Quadratic we've been dealing with. And exponential models, you've probably seen things like this when we talk about exponential growth or exponential decay. So I know we talked a little bit about this in Math 1, but we will be getting back to that, where that model is represented by some coefficient to a base value raised to the power of your input. So if your input's time, then that might be years, and this might be decaying, so maybe this is carbon dating of a certain fossil that we found, where it never completely disappears, but slowly over time is decaying closer and closer and closer to zero. Or something has exponential growth. Maybe it's a population that is doubling every year. So we start at 1, then we go to 2, then we go to 4, then we go to 8, and the longer we do this, the bigger the gaps between them are going to be, which is going to make it continuously get higher faster. So last things we need to wrap up from 12.8, we're reviewing how we use how we use the complex conjugate in factoring when we do not have real value solutions. So, if you remember what we did yesterday, this x squared plus 16 did not have a real value solution that we could find because it is not a difference of squares because that value is positive. For it to be a difference of squares, that would have to be negative. So we identify I could make it a difference of squares if I just use my imaginary numbers, and instead of x plus 4 and x minus 4, we use x plus 4i and x minus 4i. Any questions on that? Brian?
Do you want us to remember the a plus bi thing?
What do you mean? I mean, a plus bi is the standard form of a complex number. So there's the real part. Where are you looking?
Over to the left. Yeah.
Where? What?
It's
like this.
Yeah.
Yeah, well, so why we do this is we see what would be a difference of squares if the value was negative, which identifies, okay, we have some x squared and some constant squared. But I can't set this up as x plus 4 and x minus 4 because this would have to be a negative 16. So this little rule here, I mean, if you want to put a star or something, this just lets you know anytime I see that my b value is squared but it's positive, I can actually split it to its square roots by just using bi and negative bi. Okay. So it's a good rule to remember, but I don't know that you need to like formally try to like say I need to memorize this because as we do it, it should just make sense. So flip to the back. First thing we're going to do is factor out any value that can be factored out of both of them to get to a point where both terms are squares. So what on the back could factor out of both of those values? 5. 5. So take the 5 out first. I just set the pen down.
It stayed on for a second after.
So if we factor out the 5, so then ask yourself, do we have my first value as a square and my second value as a square? Yeah. So now I can set this up. I'm going to have x and x, but I can't just use 2 and 2. Instead I use
2i and minus 2i.
Yeah, a positive 2i and a negative 2i. And we want to check, why does this make sense? Well, again, my 5 would just carry. If I FOILed this, x times x gives me x squared. My outside gives me negative 2ix plus 2ix. And then I get minus 4i squared. Remember, I squared is negative 1. The opposite of a minus 4 is going to be a plus 4. So you can check that this does work out. And obviously we know that these values cancel each other Any questions? I need to restart my computer. Not like right now, but that's once it stops capturing for me. Means my computer's mad and once restarted. So now, sometimes we just straight up use our quadratic formula, right? That's our default method. If nothing else works or if I don't want to try anything else, I just use my quadratic. So what is our quadratic formula? It's not y equals, it's x equals, because remember you're solving for the x values when y is 0.
Plus or minus square root of b squared minus 4ac all over 2a. I almost had it.
So go ahead and write that down somewhere so that you remember it. So now we're going to plug this all in. So positive 3 plus or minus 9 bless you. Okay, so far so good. These values don't seem too bad. We end up with 3 plus or minus radical. Yeah, well, so 4 times 2 is 8, times 5 is 40. 9 minus 40, we get our negative 31. And over 4. So now remember, when we have division involving what will be a real value and an imaginary value, we can split. And we could look at this as 3/4 plus or minus the radical negative 31 over 4. Carmen, what do you think here?
That if we use I, we can take away, so it would equal 3 over 4 plus or minus radical 31 over 4i.
So you're saying radical 31 over 4i.
Or over 4 and
Oh, so quantity radical 31 over 4i. So also we could just leave that in the numerator then, but we would not. So how you said it, that's what concerned me, is it sounded like we were going to put it in the denominator. But, so we could just say radical 31 times radical negative 1, which then we could substitute radical negative 1 with I. So do I need to show that out, or can we make the jump that I will show it out? So this becomes radical 31 times negative 1. We then split that to radical 31 times times radical negative 1. Then we replace the radical negative 1 with the I. Any questions? So then, clean this up a little bit. I don't know, do we want to rewrite this any other way? Radical 31, that's a really awkward radical. Can't really do anything with that. Can't pull out any factors from it. Really just probably leave it like that. I mean, we could evaluate it a little bit further, but I mean, we could do radical 31. It's going to give us a decimal value, but we could do it now. But yeah, that's where we end up. Try, is there a got it below here?
Yes.
Try that, just to make sure that we're comfortable with this. So we do, again, have two solutions here. Make sure you realize the plus and the minus give you your two solutions. get under the radical?
Negative 23.
Negative 23. So when we simplify that out and use our imaginary values to represent this solution,
You want the answer?
Yep.
It would be 1 plus or minus the square root of 23 times I.
so we really want to split it up into a real value and an imaginary value. So I agree with what you said. You were going to work this one more time before you split it. But when we're looking at this as being a point on a plane, we'd want to be able to say how far on the real axis, how far on the imaginary axis. So you're totally fine, but we would just either write it like that or put the I in front of the radical 23. But because radical 23 is it's not really our coefficient, because remember I is not really a variable, but we normally put I after.
Wouldn't the 1 inside the radical be negative?
No, because it's b squared. And that's also, be very cautious when using your calculator, because if you type negative 1 squared, it'll give you negative 1, because it does 1 squared then the negative, unless you type quantity negative 1 squared, or any negative. So just be careful with your calculator. That's one mistake that a lot of my friends had in high school, not realizing that the calculator just straight up follows order of operations, and the negative counts as multiplication, whereas the exponent will then happen first. So you have to put it in parentheses and then square it. Any questions left from 12.8? Sweet. 12.9, guaranteed, will make more sense. Then I guess I was wrong. Sure. But I think it will be easier, so I'm still hoping it will be easier, even though you want Candy. So when we talk about linear functions, what's one thing that we know about our linear functions? Actually, so let's back up. What's one thing we know about any functions? We have a pretty strict rule about functions. I guess I should capture this real quick. What would make something not a function, I guess? That's an easier way to talk. How do we check functions? Like if we're looking at a graph, Megan? Yeah, which vertical line test is really telling you every function, for every input, there's a single output. Right? So for every input, there's a single output. One output could share multiple inputs, because if you think about parabolic, one output shares multiple inputs. But for every input, there can only be a single output. So if we look at this stage function up here, we're saying this is a function. We have input 1, input 2, input 3. My inputs are my stages. So I can say, well, okay, input 1, I get an output of 1. Input 2, I get an output of 1, 2, 3, 4. Okay. Input 3, I get an output of, all right, now my bottom layer. Well, I still have 4. Really, I'm just adding on a new bottom layer every time. So I have my 4 triangle plus 5 more. I get 9. So what if we want to predict stage 9? And we really do not want to write this out, like every single stage. That would be arduous. This is like a math counts type problem. Calvin, what do you think? What do we look at here? Oh.
Can I start out by saying what it is?
I mean, sure, but you're going to have to justify with how you know.
I think it's 81.
Okay, so we are hypothesizing 81.
Because for the first 3, the number of triangles is the stage number squared.
Okay, so the number of triangles is the stage number squared. So if we're still just hypothesizing all this, so you're saying my output will be my input squared.
Yeah.
So if I added on a 4th row, then that would make the first triangle over here upright. The first triangle over here upright. Then how many between them? Like, how many are really getting added on every time? How can I talk about the change between each stage? Caleb?
I was gonna say, well, by looking at just how many are added at the bottom row, it goes from like 3 to 5. So I would assume 7 for the next row.
So we had a change of 3.
Yeah, it adds
Then we had a change of 5. So the change in my change, what you're really identifying is the change in your change, is that we got 2 extra. Sorry that you can't really see the green that well. We got 2 extra between those 2 sets. So we're hypothesizing that we would get 2 extra on this set as well, which would mean that going here, we would add 7 is your hypothesis, which would mean that stage 4, would it be 16?
Oh, no.
So then stage 4 would have 16 triangles.
And then you got that.
If this holds true, then my change on the next one gets another extra 2. So that instead of adding 7, we'll then add 9. Would that give me my next perfect square?
Yes.
Yeah, that would give me 25. So this is working out that will be my function. Now this is the parent function, the original of our exponential. Because this value will continue to increase. Sorry, not exponential.
That's the parabola.
Yeah, that's the parabolic. Sorry, I said the wrong thing there. So if you compare parent functions, this is like the right side of your parabola. I just don't even care anymore about straight lines or anything like that. If we went into the negative stages, it wouldn't make any sense. So even though this is a quadratic function, we don't think about it as the entire parabola. We only care about the positive side. So if we think about exponential situations, it involves the base to the power of your input. Anybody think, I don't know if you guys have seen any examples of exponential type situations. You had this in science class or anything?
Yeah.
Oh, like things like finance and stuff.
Finance uses exponentials.
Yeah, they're interesting.
Carbon dating is one of the most
Like
applicable.
half-lives.
Half-lifing.
Yeah. We did that.
So if you guys have done half-lifing, then you understand the basics of our exponentials. Because it's like the idea if I am going to say that every step or every stage, I go half the distance to the door. That whole idea. Or half the distance to non-existent. So if I'm talking about half the distance to the door, I could go one stage and go half the distance to the door. So whatever distance I started at, that's like my y when x equals 0. My y would be whatever, 20 feet, I guess if we want to say. So I go half the distance. My stage 2, I'm now at 10 feet. I go half the distance. I'm now at 5. Half the distance now at 2.5, then 1.25, and I keep going half. Am I ever going to reach the
Is there
door?
anything about Achilles with that, where he said he did a race where they can only do half the distance every time, and he somehow managed to finish the race?
So this is the problem with theory.
It's the arrow. If you take a picture of an arrow flying towards the target halfway each time, if you do halfway each time, the arrow will never make it. But we all know that the arrow will make it.
So it's the difference between theoretically. So this gets into the idea of limits. Now, limit functions are a little bit different, but limit functions are explaining like the limit, the value that this can never reach, but it gets as close as possible as you go out to infinity. As your input values, as your stages or your steps or whatever you want to say, as your x goes out to infinity, it gets closer and closer to a certain value, in exponentials, most of the time we're talking about 0, or it exponentially is getting larger and larger and larger, so this line is becoming almost vertical. So you're either becoming, it'll look vertical even though it doesn't actually become vertical, or it will look horizontal even though it doesn't actually become horizontal.
I know a funny joke about limits.
Okay?
An infinite number of mathematicians walk into a bar. The first one asks for a pint, the second one asks for half a pint, and on and on and on. And then at the end, the bartender just hands them 2 pints and says, "You guys just don't know your limits."
Because if you add up all the values, a pint plus half of that plus half of that, you'll never get over 2. Because the halving, you're filling the second one half, then half, then half, then half, then half. So if he hands them 2 pints, the limit would be 2. Because you started with 1, then you added a half, then a fourth, then an eighth, then a 16th. That's pretty fun. I like that a lot.
I didn't hear it.
I didn't figure you would have. Hopefully you've never had a pint. So, one really good thing to do when we're looking at these values is to set them in a T-chart, but order your points. So, I have x values from -3 up to 0. I'm going to put them in order here. Sorry, up to 1 actually. And 3, 0, -1, 0, 3. So we can evaluate the behavior of a function either by looking at the points graphed or looking at the output trend or the output behavior. So I lose 3, then I lose 1. What does that immediately tell me my graph isn't? Linear. Because this change is staying consistent, and to be linear, this change would also have to be consistent. So we immediately see non-linear. Then I add 1 and add 3. So this really tells me that right in here we have our what? Our vertex, where our behavior changes and does the opposite of what it had done before. And when my behavior can change and do the opposite, that means that my graph is quadratic. So if we plot these points, I would have 0, 0, and -1, -1, -2, 0, -3, +3, and I also have 1, +3. And we get a graph that looks something like that. Any questions? So now let's set that up for B. Take a second and try to evaluate on your own, looking at either the points when you put it on the graph or the behavior. I like to look at behavior first, because sometimes points on the graph sort of gives things away. And I want you guys to be able to just I want to save you work. If you were only given the T-chart, I'd like you to be able to look at behavior and identify graph type just based off behavior of input versus output. If I evaluate behavior, the change in the output is not consistent. The change in the change of the output is not consistent. So our example problem that we solved, the change in the change was always adding 2 extra every time. And that gave me a quadratic or a parabolic relationship. So now this level 2, or the change in the change, if you want to call it delta delta, you can. Because really, when we look at delta, if delta is consistent, it's linear. If delta delta is consistent, it's quadratic. And if it's neither, it may be exponential, but we would need to check by completely changing the math that I'm doing. Instead of looking for the change algebraically, exponential functions behavior change geometrically.
Nice, Dave.
Thanks for being the third person to finish the sentence. Appreciate it.
I was thinking
Shoulders.
first.
No one wants to see shoulders.
So now, instead of comparing using arithmetic, try the multiplication. So if we look here, we'd be multiplying by a half. We're multiplying by a half. We're multiplying by a half. So when you have a multiplication change or a multiplicative ratio, a consistent ratio from term to term, that tells me that we will be exponential. So if the arithmetic isn't showing me anything, look for a common ratio. Easy way to do this also is you can change which direction you're working. So if I go up, I can see that I'm doubling, which is pretty easy to see. Sometimes the ratio in fraction form is a little hard to see, so you might want to go up the bigger values, and sometimes that's easier. So if I plot these, we'll see that it behaves like an exponential. I have 0, 2, negative 1, 4, 1, 1, 2 and a half, and if I keep plotting this, I am not on my line. I'm not on the x-axis, but I'm going to get infinitely closer to it to the point that you physically can't see the distance between them, but we know that this will never reach it because when I continue to half, I can't get 0. Because I started with a value. There's no way that I can get to 0. So my limit there, when you get the limit functions, our limit would be 0. Because I cannot reach 0. I cannot ever get to it. I get infinitely close, can't get to it. Yeah.
Can an exponential function like add a c value?
Well, so the original exponential would be our y equals a times b to the x. So if you added a c, so in what application do you think we would add a c value and shift it vertically?
If the value that it can never reach isn't 0.
So this is where the idea of limit, so like your situation with the bartender joke, that would not have a limit of 0, that would have a limit of 2, and it's actually coming up, right? So it's exponential, but that's where limits are different than exponentials, because that's not exponentially increasing or exponentially decreasing. It is growth with a limit of 2. So yes, there are situations, but it depends on the application. I don't want to go too deep into it now, but short answer is yes.
Because you kept saying 0, and I get that is for this situation, but I was wondering if that didn't always happen.
Yeah, no, in other situations we would use other things. Like let's say you are managing a stock room and you never want to get below a certain amount of items, then that would be like your limit amount. And if I have, this decay that we've sold, when it first came out, we sold this many, then the next day we sold half as many, and then like when I get closer to that value, then I have to reorder. So I don't want to ever reach that value, but I could get close to it and I don't really mind, but I don't ever want to reach that. that's not really the greatest example, but just what I can think of right off the spot. We, at one of our math meetings, looked at how you could actually, and I should get this problem back from Mr. K, how you can look at the salary of hockey players. And you could look at how many goals they score per game compared to the salary that they make. And so the problem was, and I'll try to get this problem from Mr. K, but the question he was asking is, could we create a mathematical model to determine the payout for the players based off a function model that we understand? So linear wouldn't exactly be, that fair, because you kind of don't want to say, well, if you have a really great season and you score a lot of goals and we have this linear function, well, we got to pay you way up here, we're going to run out of money. But if you think about it exponentially, again, these guys that get a low amount of goals don't get very much pay, and then these guys get all the pay. So I don't want to give it away to you, tell them too much, but I'll try to get that problem. It's a really interesting situation.
Wouldn't that mean you have to pay them
Wouldn't it be
after the fact?
Yeah, you would not know your pay going into the season. Your pay would be determined by performance.
Oh yeah, that'd be a lot of motivation.
That'd be a lot of motivation.
So the problem is looking at like Rick Nash, right? Like, what does Rick Nash make versus how many goals does he actually score? Should he make what he makes regardless of performance? No, probably not. If you sign a contract for X amount of dollars and then you perform like crap, there should probably be, like, if we signed a contract based on a mathematical function of my payout will be directly related to my performance, there's your
But
motivation.
it also kind of like screw over, if someone did really well, it kind of screw over all the other people. Even if they
No,
did just as well.
because if everybody was using the same function, how well you do does not negatively impact me.
No, but like cap limit, like
Yeah, they would
Yeah,
just
like,
like
there's
But the better the players do, the more tickets that get sold, the more money that gets made, and the more money they have to pay
But
the
there's still a
players.
limit. Like if every player does very well and they just dominate the entire season, they're not going to have they're still going to have a cap. So if you go by that, there's going to be certain people left out.
like you can't make.
So
the
let me
$7
get this problem,
million
the formal problem from Mr. K. Hopefully he still has it. Let me try to get that problem. We'll look at that on Monday.
No, but a team can only spend so much money per season. They
Yeah.
can't just spend all the
Assuming that your income is fixed. Income is only limited by how many seats you fill.
money. No, the team can only spend a set amount. They can't spend any more or less, no matter how many seats they sell.
Isn't that like a thing set by like?
Yeah, it's
that's
set
So
by-
I agree with that. Like, right, our money is not infinite. Right? I can't just say I'm going to keep paying you X. So this is where the idea of limits
Oh,
comes.
so maybe like the limit could be like an increasing, but then there's a limit of you can only play this player so much. So
Like no matter how well.
so it would motivate the player to get to that point, but then they would just stop.
Then
playing.
This is where we look at manipulation of exponentials. What happens if I take this exponential curve and ignore this is not problem C. But if I did this, but if I flipped that curve and make if I score 0 goals, I get $20,000. Maybe that's my point. As I score more goals, I'm getting more pay. But once I get up here and I've scored lots of goals, every goal should not continue to be worth the same amount. Right? The first goal that I score in the season should be worth a decent amount. That's great. I scored a goal. Next one, not as important. I've already done well. The next one, not as important. So this gets in the idea of should then every goal, once we get out here, be worth less and less? And I'm still making money.
But maybe it
but
would motivate the other
less-
players who haven't scored to play more. So
And it
they-
could motivate me to pass the puck to you because my goal might only be worth $1,000 now because I've scored a bunch.
that person
But if I
might
kick it over to you,
$20,000.
yours might be worth $10,000 right now
But if you-
because you haven't scored yet.
But
Does
then
he
it-
hate the person?
Yeah, then
that
you'd
passed
also
the
then
puck
there'd be
to
a lot of
you?
animosity between teammates. It'd be like, oh, you didn't give me that. Now I'm losing $30,000.
Well, and so do we just want to make money or do we want to win as a team? So we'll talk about this Monday. We got to keep going. Ethan?
My question to you is like limits. Like, have you ever heard the problem with 1/3 and like 1/9 with 9 thirds? Like, following the pattern that it goes by, 9/9 is worth 0.9 repeating, but it's also worth 1. So that's
There are multiple ways to prove that 0.9 repeating is actually equal to 1.
yeah, I've heard that, but
That goes deeper than we really have time to go today. I don't even know. When are we over today? 50. We got 10 minutes left. Okay.
Are we? Can I still have a question about the hockey
Yeah, so that could not operate on the same function. So we'd have to have different functions depending on the player.
No, because that depends on.
The other team.
Right, and if I'm a
The
defensive
defense.
player primarily,
So maybe say percentage.
so let me see if I can get the real problem. So when we just talked about this at a math conference because he was trying to teach this content, so the head of the math department for Worthington used to be a high school math teacher. He taught this content. Like, that's a good thing. So he said this problem like kind of just organically happened because they started looking up the pay of the players and they just started putting them on the graph of like, what can we compare? Well, how many goals did they make? How much time did they play during the season? Like, what things can we compare with the amount of pay that they made? And this function kind of just like came out of it. So let me see if I can get all the details. Well, let's look at this guy. If I just plot the points, well, I've got -1, -2, 0, -1, 1, 0, 3, 2. Carmen?
It's linear.
This is going to be linear because we see that our function is creating a consistent slope all the way up. So when your delta y is consistent, that's a linear. When your delta y is consistent, that's quadratic. And when the ratio is consistent, that's exponential. Oh, come on. Don't be mad at me. Try the got it real quick. Now, if they're nice and put your points in order, it's a lot easier to look at when I just like look at the paper. Because if this was nice and I went from -1 to 0 to 1 to 2, I go from a half, negative half to 0 to 1 to 3. Here's the other problem, though. I have a 0, 0 point. Now, if I start trying to use a ratio,
Not gonna work out.
so let's plot these.
Wait, well, didn't you say that you add by a certain amount and then that amount increases or decreases depending on what the x value is?
So if I do -1, -1/2, right about there, 0, 0, 1, 1, 2, 3.
Oh, sorry.
So if I just start looking at the delta, got a half, then I've got a 1, then I've got a 3.
Up by 1/2.
Or sorry, then I've got a 2. Sorry.
Up by 1/2.
So my change in my change, this went up by a half. This increased the amount. Ooh, crap! That went up by 1. So the change in the change is not consistent. I love Pettigrew. I don't know, guys. What do we think? No. About this, Brian.
Would it be like the same that we did with the quadratics? Would you just like subtract 1 and then that would move the whole graph the line down?
Sure.
Okay.
So are you hypothesizing that this point would potentially be like our vertex then?
Well, then -1 would be like the new 0 for that. It'd be like the limit.
Wait, so you're saying quadratic or exponential?
Exponential.
Okay. So what if -1 is my new 0? Okay, so how? So what what are you trying to do with that then?
Well, I mean, I don't know.
Like if I told you to think about what the next point would be, try to make a
It would be
hypothesis.
half. It'd be half as close to -1 as that one.
Other direction.
Other direction. Oh, it'd be twice as away from -1 as
Twice as away.
that one.
Caleb?
I was thinking that it's sort of like it's an exponential function, but you base the so like in exponential functions there's like a I wrote it somewhere. Oh yes, it's a times b to the power of x.
So this might.
But I was gonna say like it instead of b being like a I think b is a fixed value. Or I think I'm crazy. I don't know. I just know there's a. I think there's a 1 somewhere.
Yeah.
Because I know it's 1 to the power of x, which I think is somewhere in the equation. Because if you look at like, I'm just crazy. If you look at like the math, I think it works out. But I don't know.
Okay, I like what you said. Calvin?
I think when x equals 3, y would equal 7 because I was messing around with the equation and I got y equals 2x minus 1.
There was a 1
I
there. See.
The c,
So 2x minus 1 would be linear though, wouldn't it be?
or 2 to the power of x.
Ah, so you're saying that your y equals 2 to the x minus 1.
So our
Yeah,
c
that's
value
how it
is
would
negative 1.
So the a value then is just 1 as well. So hold on.
Pretty great.
What happens to a number to the 0 power?
It's 1.
It goes to
It's
1.
1. But when I have the input of 0, I don't have 1, I have 0. Here's the method you want to think about, and I'm going to pass out your homework. I mean, we've got 3 minutes left. Is it linear?
No.
No.
Is it quadratic?
No.
No. So it has to be. If it fits into one of our standard function models, it's got to be exponential. So the question from there is, how do I fit it into my y equals a times b to the x? The first thing you want to look at is when my x is 0, how do I make this happen? Well, it doesn't matter what this number is. When x is 0, this will become 1. So to get my output to be 0, this has to be a minus 1. Then I can figure out what's my base based off, okay, when I have a power of 1, what did I get? Well, I got an output of 1. Well, 2 to the first power is 2 minus 1. That works out. Check it with, I plug in negative 1. Well, remember, negative powers, this would really be a half minus 1. It works out. So this
I was close.
is going to be the model of our data, where our limit here, because we don't really know much about limits yet, so I'm using that very loosely, but our limit would be that negative 1 value. Instead of being 0, like I forget who said it, negative 1 is our new 0. So, very good problem-solving method, guys. Your homework is here. It is not bad. It's 17 problems.
Ryan, we have science.
A lot of these, if you put them in order and then evaluate the delta y, the delta y, they're pretty easy to figure out.
Oh, I don't know why, but I was thinking that you were No, I know.
You're after it,
I don't know why, but
Have a wonderful weekend, guys. We will pick this up on Monday. Obviously, continue working on this. It just doesn't matter. We don't show it because it only happens if you need it to happen. I mean, I agree. If I was, no, because it's always there, even if it's a 1. So this,
always there, even if it's 0.
well, but if it's 0, then it's not there, right? 0's lack of quantity. So there can't be a 0 for your a. Like, and I think the rule with that is a times b to the x when a and b cannot be 0. Yeah, if you can. That, like, and just show 3, 4, 5 points. That's good enough.